Now, today we're going to be talking about the pictures of math. Okay? The pictures in math, you know how they always say pictures worth 1,000 words. Graphs could have over 1 billion pieces of information on one graph, whereas charts, you're limited to obviously the font you're going to use, how many things you can put in the chart, how big a page you want, all those things. The trick we're going to be doing today is, can you take information and make a picture? And can you take a picture and get information from it? Okay? Those two are quite critical. Now, I just want to throw out a scenario for you. Okay? Okay, someone breaks into a home, and they go through the home and steal a bunch of stuff, and then they leave. An investigator will show up, and he will take a lot of pictures. Now, tell me, let's think about it. Let's think about it as a class. How are those pictures going to help catch a guy? Like, what is the mess going to help? What, like, yep.
Because then you can like re-look over and stuff.
Yeah, but what would you look for in those pictures? Okay, what kind of evidence? Give me something that would say, this is specific to this guy. Yeah, but I don't know, would that be specific to a guy? But you're right, he might have dropped something of his own. And they see it there. Okay? What else? Okay, but give me some patterns that you... Exactly. And you know what? I'm giving you a true example here. This is a real example. And exactly what you were saying. Left the big screen TVs, the iPads, the iPhone, a Samsung Galaxy. I can tell you, left it all behind. Took just gold, silver, and diamonds. That's all he took out of the house. Okay, so diamond rings, diamond earrings, gold, silver. Ransacked the house, just took that, and any money, cash, and meds. Okay, because they have street value. That's what he took. So, that's more verbal evidence, but how could pictures help you? Why do they take them? It sounds like it's a waste of time in our class, right? Could this class figure out anything with those pictures? What would you take, if you were taking the pictures, Haley, what would you take pictures of? Yeah, but they will ask you, do you have any pictures? Do you have any receipts? Do you have any, right? But can I even back it up a bit more and say you're the investigator, you're taking pictures? What would you take pictures of, you guys? How he got in. Why does that help? It shows maybe how he gets in all the time, right? Because their MO, have you ever heard that? Yeah. What does MO stand for? Operandus or something like that. It's all, yeah, Google it. Their MO, it's medius operatus or something like that. But it's funny because criminals have patterns, and taking a picture of the door, they can actually say, it's this guy. Modus operandi. Modus operandi. That means they do it the same way. Their MO is that they, like this guy goes through patio doors. Finds a patio door and he goes right through it. You know, he does not open the patio door. Do you know why he doesn't open the patio door? Because it's alarmed. So, and he doesn't smash it hard because there's also sensors that'll pick that up. So he pries, then he makes a big enough hole, and he goes in, steals everything you have, ransacks your house, and then leaves. Yeah. No, believe me, it doesn't use a laser, okay? Because you can see the pry marks on the door, okay? So you take pictures of that. There was also a bit of like whatever he used to pry it open, a bit had broken off and was on the ground beside it, like part of the handle, part of the rubber handle. Okay, you can also take pictures of, because if you take pictures, you can see the size of the hole, and you can see that the lock was still on the patio door. Okay, so you know he gained entrance by just going through it. Okay, not by opening, because a lot of people smash, they open the door, and then they get in, right? So if you were just given pictures, could you say if it was the same guy that you had last week or the week before? Okay? Now, we're going to be starting with just interpreting graphs. Now, this is a graph of a guy taking his dog for a walk. Dude. Now, I think all of us would say, that's ridiculous. How can you graph taking your dog for a walk? Okay? But this is, you know how when are we going to use this one? If you ever get into, well, everybody's into it now. They're using their watches for all their fitness stuff. So if they go for a run, like Nike Run they'll give you an entire graph of your run. Okay, so here's time, here's distance, your speed, pulse rate. They can give you a graph of your pulse rate as you go. They'll give you all that from one run, right? Because if you're wearing the watch, and then you can just put a little pod in your shoe, okay? And it's fun. Everybody's doing it now. They're graphing their day, how many steps they're taking. All these fitness watches, they're a craze. They're huge. It's probably going to be one of the best-selling, small things this year. Are all the fitness watches. You just watch. Now, so this is what your watch would look like if you took your dog for a walk. Okay? Now, I want you to look at it. It's very important you look at the X and you look at the Y. X is, and this is Y. This is what we usually call the manipulated variable. And what's the Y? Responding, right? So usually the manipulated, that's the one the researcher controls. So like if I was seeing what was the best fertilizer and I had 10 plants, I would control the fertilizer. The Y would be how tall the plant grows. Like I don't have control over that because I don't even know what fertilizer is the best, right? So always know where you're starting. What do you think this is right there? That would be home, right? Yeah, the class I drew home, but they didn't appreciate it very much, I don't think, with their laughter. So I'm scared. Okay, so I will just write home. Now, look at the times. We want to look for consistent pieces. So do you see from here to here? Okay, that's very consistent what's going on there, isn't it? So this would be from 0 to 12 seconds. Now what's happening from 0 to 12 seconds? Minutes. Okay, so walking, what's the rate? No, we can do better than that. We can tell exactly what the rate is. 1 kilometer to 12 minutes. Okay, you won't need a calculator. You'll be fine. So, if you were just Like, this is what I would love to have done with you every other time, is just say, tell me what's going on. Like, tell me what's really going on. Okay? So now, you're just walking your dog. Now, next, we've got this interval is very consistent here. And this would be about, what, 12 to, let's say, 18 minutes. What is happening on the graph? What's distance doing? He stops. So he stops. Now, this is what police have to do. They have to try and figure out why. Why do you think he stopped? He maybe had to pick up poop. Yeah. How long do you have for? Yeah. So we might have dog going to, we'll say, washroom, because people around the world will watch this video. I don't know. Okay. So dog's going to the washroom. So this part here, that's not on the graph. That is purely by using your experience, your knowledge. Like, why would a guy stop for 6 minutes? He wouldn't just stand there for 6 minutes. Okay, dog, wait. Right? There's probably a purpose. Right? So this is what I'm talking about. We're not just looking at a graph and going, oh, stops from 0, you know. We want to know what could be happening. Okay. Then we've got, oh, that should have been there, sorry, right there. And then we've got this interval next. And that's about 18 to 24 minutes, right? But what's happening there? Running? Okay. Ah, okay. Maybe he did. Maybe he dropped the leash. See, this is being very interpretive. This is exactly what investigators do. They sit in a room with a bunch of people and they gather all the evidence. Why did he stop here? Okay? Why is he always stopping here? Okay? So then they could find a pattern of, like, that police officer, or sorry, they have caught that guy now. Okay? And now they're trying to find out where he lives, obviously, find out all the safety deposit. He's getting rid of that gold and those diamonds somewhere. It has to be a jewelry store, so they're staking out a specific jewelry store. Okay? Have they found any jewelry on him? No. Okay? How did they say this guy is our guy? Those meds had a name on it of one of the houses that he took it from. So now we know that's the guy that's to that house. Okay? So let's just say he's not getting out of that one. That's pretty good solid evidence. Yeah, it's case closed, but there's a lot of stuff that is not found. And the police have two objectives, obviously. One, to catch the guy to stop doing it, but he wants all the stuff to come back to the people. Right? So that's why they're always looking for patterns. They're always looking for, like, interpreting what's going on. Now, if he dropped running, at what speed is he running?
1 kilometer.
Yeah, a little bit more. So 1.3 kilometers to about 6 minutes, right? Okay, and then what's happening from 24 to 50 minutes? Okay, walks. So maybe, okay, walks the dog. So what do you think happened? He caught the dog. Yeah? The dog's like, yeah, I'm going to get hungry soon, so I do want some food. I want to stop and get home. Okay? Now, what is this of? This is a distance time graph. So do you think he's far from home now? He could have done a loop. See, it's not distance from home time graph. Because a distance from home time graph is very different than distance. Okay? So if you drive for 100 miles and then come back for 100 miles, your distance away from home is 0. But how much would your odometer say? 200. Okay? So don't get distance from home confused with total distance. Okay. Oh, well, this is exactly what I'm talking about. Now we're at distance from home. Okay, now that's very different than distance. Does he start from home? No. He probably walks. Okay? A lot of people, when they're going to go for a long run, they will walk for a bit just to get warmed up. Because if you just go, it's like getting into, if you just start running right away, it's like getting into I would always say this, I used to teach running clinics or whatever, and people are like, yeah, if I start too fast, I'm just like uncomfortable the whole run. And I go, you know what, have you ever gotten a vehicle, right? And you're listening to some tunes, and then an awesome tune comes on, and then you crank the tune, right? Park your car. Then the next day you get in, and the tune starts up, and you're just like, oh man, and it's just cranked, and it's just like, oh, and you turn it down. It's the same thing. See, if you're driving along and you get used to the noise level, and then you turn it up more and more and more and more. But if someone just blasts you with that, it's like uncomfortable. Yet it was the same, like that was you that left it at that volume when you left the vehicle, right? And you know, like that happens all the time. Okay? I actually had a vehicle that would turn it down every time. It was all programmed in. It was kind of nice because my one now doesn't. And sometimes you listen to a good tune, you park, and then you get back in it. It scares the crap out of you, right? So anyway, he walked. So he's starting 1 kilometer from home. Tell me what is going on here. Let's call this interval 1. What's going on at 1? That would be from 0 to 20 minutes. Okay, what's he doing? Jogging, like be specific though.
Jogging away from home.
So he's, let's say, running away from home. That sounds bad that way. Away from home. Running away from home at a rate of 1 kilometer for 20 minutes. Yeah, well, you know, starting out nice slow too. Yes, it's uphill, it's windy. Snow is like hitting him in the face. He's one tough runner. Okay. Now, what's going on here? Okay.
He's running a traffic circle. He's running parallel.
No. If he's running on a traffic circle, this would be, if he continued running, he would be running on a treadmill at this point.
Yes.
Do you understand? Distance has not changed, but time has. So there's lots of things that could be happening. Rest.
Rest period at the bottom.
Could be rest. It could be, and I used to do this a lot because I used to live pretty close to the Kinsman. So I would run to the Kinsman, and then you do a workout there. Do you see that no distance will change the whole time you're at the Kinsman? So, like, I've even thought, like, if you go down, we have like a workout room in our basement, right? Got the treadmill and got the bike and everything. If you go down, if you ran 5 miles on the bike, ran on the treadmill, biked like 10 kilometers on the bike, you have moved 0 distance. You've done absolutely nothing, and yet you're sweating and feel like crap. Okay, so you haven't moved, but that's what that distance over time would be. So, too, you could see rest. He, went to the gym. So you can't always say he just stood there, and I think that's what people think. Because if you're at a place the entire time, maybe he met somebody for, and he's talking, right? Or ran to someone's house to drop something off, and then they got chatting, okay? So it's just not standing. Then what's happening in interval 3? Okay, so he runs home. So this would be from 40 to 50 minutes. Runs home. Quick. Okay. What would be the speed? In 10 minutes. What's the question? Yeah, that was 20 to 40. Okay. So, how do you, by looking at a graph, know that he's running faster? No, I'm not asking what could be happening to him, but yeah. And what's that called?
Angle of...
Nobody knew this in the last class. What do you call that on a graph?
Because he's on data.
The steepness of a line is called the... Starts with an S. Slope. Nice. Okay? The steeper the slope, see, what's happening? Let's actually think about it. Yeah, get off your dog, man. There is a little bit of time happening and a lot of distance. Now that's kind of your goal, isn't it? Anytime you're like in a race, don't you want the distance to be great and the time to be little? Okay, that's how you win a race. If your time is smaller than the time beside you who ran the same distance, okay, your slope would be quick. So yeah, maybe we've got the dog chasing. Maybe more likely, I would say, is that person looks at their watch and they go, whoa, I got to get home quick. And do you see how they are at home now? Why are they at home? Look how far away they are. They're at 50.
That's time.
That's the time. Do you see how they've actually come back? Well, they didn't start at home, but that is a graph of distance from home / Okay. I want to just give you a couple minutes. I'm just going to pause here. And I want you to match. Okay, so obviously you guys are too good at this one. So graph A belongs to who up above? Tree. So can somebody describe why this works for a tree? Yes, what's...
Because you're growing up in more time.
Yeah, but it's not this. So tell me why it's not that. Okay, I'm asking Winston. The rest of us are this walker.
It doesn't grow perfectly up. Like it depends on like conditions.
Okay, but what's happening here probably?
It's
coming from maybe a seed, right? And if you've ever watched a seed grow, it's not a good time. Okay? It's boring and arduous, right? So it goes really, really slow, then it goes boing, and it pops out of the ground, then it starts to grow. Okay? And then as it gets older, it will decrease in its growth rate. Okay? Graph B would belong to? Oh. Okay, so we're picking C. Yes, sir, thanks. Now, I told this to the other class because I thought this... No, so this would be height, and this would be the tree. This would be the temp, right? And this is time. If you ever watched, coffee or whatever hot drink, they cool down quite quickly, and this would be the graph of that. Turn this way, so we're... Now, there's this, if you ever watch Shark Tank or Dragon's Den, either one of them, but these guys had these things on, and they called them joules, because off of the joule, right? Joule's a measure of heat. And they were silver, and they're, you know, about the size of, say, 2 ice cubes put together. And inside, so they were like stainless steel, and then inside they had their formula, and it wasn't poisonous. So even if that broke open, out of whatever chance, it would not hurt the person. But what they did was, and I don't know my temperatures, but say the perfect cup of coffee is like, you know, 80 degrees, right? 100 is boiling. Let's say 80. Well, when you have boiling water, that's 100. And when you pour it into coffee, it's too hot for a while. You got to blow on it. Well, these Julies, you have about 3 of them in the cup. And what they do is they instantly take that coffee down to 80 degrees. And it keeps it within it. And then as the coffee starts to cool, it releases those joules. So it stays 80 a long time. Okay? But they haven't come out yet. I haven't seen them out yet. Usually I can see stuff on there, whatever, and then you can see it like a year later. And yeah, I saw that on Dragon's Den. But, and I was thinking, you know, the problem with them is A, they were expensive, but B, they did take up quite a bit of the room in the cup. And I thought, well, what if you could actually make the cup out of that stuff? Let it absorb, and then it would put it back in, right? That's, well, no, but if you had a nice insulator on the outside, right? Yeah.
Like a Julie thermos.
A Julie thermos, right? But maybe the chemical inside they did find out was poison or something, because it's still not out yet. I've seen that a couple of years ago, but that one I'm like, that is going to do well, right? If you could just instantly pour your coffee in, have it at, what's that? Oh, they went nuts. They're like piranhas, like sharks in the Shark Tank. Hey, this one here. What's this one? Okay, so this is Calgary. So this would be temp in Calgary. That's D. So what happens is this, right? This is called sinusoidal. We'll talk about this more, but it keeps continuing the same pattern. Okay, it's a periodic function because even though the temperature in Calgary is not the same day every day, like every February 5th, it's not the same temperature. It has an average temperature that is very consistent. Okay, so you can see where this would be, you know, height of summer, and this would obviously be winter. Okay, and 0 is your. Okay, ladies, can I continue here? You have to talk later. Okay, now the next one would be the bungee. Now what would be the Y value, height? Have any of you ever bungee jumped? I did it on Vancouver Island, over a bridge, into water. It's, you know what? When you're jumping, you're going, this is the stupidest thing I've ever done in my life. Like, you know what? This is what I thought. I bet you people who like commit suicide right after they jump, they go, crap, I wish I would have done that. Right? Because after I jumped, I'm like, crap, I wish I, well, what do you do now? Right? Yeah. So, like, when you jump, you're like, yeah, this was stupid. I shouldn't have done this. But then it's like, then you're going straight for the water, and it just sucks. But then you start to slow down nice, and when you go into the water, it's just like you go in, and then you get pulled back very slow. It's not boing like a yo-yo, right? So after that, it's not so bad. But the first jump, like I've also jumped out of an airplane. When you jump out of an airplane, your chute opens right away. It's like relaxing. I mean, jumping out of the airplane's hard, okay? But you don't really. You don't see, the ground isn't coming at you like bungee jumping. Like bungee jumping, the ground's coming at you the whole time, where when you're up in an airplane, you're so far up that the ground's not rushing towards you, right? So when you jump, I mean, it's hard jumping out of the airplane. That's the hardest part, right? Especially when there's something, you know what's worse? When the person in front of you is freaking out. I don't want to go. You're like, go. Would you get out of here? You're freaking me out now. Right? You're like, okay, can I go? And then you deal with her, right? But so that's the worst. But it's nice. As soon as you like follow your chute opens, it's extremely relaxing and it's cool.
Once your chute opens.
Yeah.
Chute doesn't open.
Yeah. Okay. Now this question is a really, really tough question. Okay, so we have to pay attention, ask questions where we can, because I need you to understand this really well. So we went slow with the other, and people weren't talking. Okay, if you have a question, just need to put up your hand. Now, Sakura leaves home and travels at a steady speed of 100 kilometers an hour for an hour, slows to 80 for half an hour due to construction, then continues for 110 for another hour. She stops for a 2-hour meeting, and then she returns home at a steady 100 kilometer per hour rate. Sketch the graph for each scenario. Now, do you see the scenarios, Haley? Don't talk, please, okay? Speed versus time, distance from home versus time, and distance traveled versus time. Now, these are 3 graphs that most students would probably not attempt, okay? They would just be like, I have no idea how to even start these. Well, as a class, let's do speed versus time, okay? Now, it is, like, draw your graph, right? This is going to be speed, and speed will be in kilometers, and this is time in hours. Now, what are our increments? Like, what should we be going up by? 10? Okay, because what's the fastest she goes? Okay, so if let's go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, we'll have to add zeros to all of those. Okay, so up to 110. Okay, so far so good. Now how much, or how would you go on the bottom? Like how many hours should we even go? You want to go every half hour? So we could go like this. So that would be 0. And then you can go like this. 1, do a tick. 2, tick. 3, 4. How far should we go? 5, 6, 7. Go 8. Try that. It might not be enough. We can add to it. Okay. Now she leaves home. Okay, so 0, 0. 0 speed, 0 time. So that's a good place to start. She leaves home at a speed of 100 kilometers for 1 hour. How would you do that? Yeah, so basically, she's starting kind of here. Now I know what you're thinking. You just can't pin it and go that quick, right? But there would be a little bit of a. She'd have to start at 0, but it would go quite quick because acceleration. Because you can get you can do 0 to 100 in like a fast race car in 4 seconds, right? So this is per hour, right? So let's say it's taking 10 seconds. So now we're going to go like this for 1 hour. Okay, so let's call that 1. Okay, so now slows down to 80 kilometers an hour for a half an hour. So then I am going to go down to 80, and it's going to be quite abrupt because you can slow down 20 kilometers in a car like that, like in a second. Okay, slowing down 20 kilometers is you wouldn't even be jerked in the vehicle. Okay, it'll have a tiny bit, but just remember this is hours on the bottom. So you're not going to see much of an incline because seconds on an hour graph don't show up that much. So that's why in school zones it's 30 kilometers an hour. Because if any kid runs in front of the vehicle, your reaction time, your vehicle, right, there wouldn't even be a skid mark probably at 30. So it's funny, I've thought about this. I'm just telling you that, you know how when you had the horse and buggy, it was like 10 kilometers an hour, that thing would like walk and, you know. And then they invented the car. Now what if the car only went 30 kilometers an hour? Now that's 3 times faster than the buggy. That's cool. And no one would die. Like if everybody was driving around 30 kilometers an hour, like even if you had a head-on collision, you'd be like, oh crap, that hurt, right? And it's funny, right? I think about that. Like if we lowered the speed limit to 30 kilometers an hour everywhere in the city,
It took so long.
it would. And you know, that's why they don't do it. It's still 3 times fast. And it's because we would have to come from like 60 in the city down to 30, right? And then we would be used to that. No, this sucks and the whole thing, right? I got places to go. I got whatever. But it is, I think, a balance between, and this may seem, but I know this is how governments have to think, speed limit and deaths. Because the higher your speed limit goes up, your slower your reaction time, right? Obviously now, if you're driving something at 110 and you hit the amount of momentum there, my good friend of mine used to be well no, he still is a firefighter in Red Deer, and they one time had to, the guy had some pens, you know, just sitting on the back of the, you know, back of the car, and when he hit the brake, or no, when he hit on head on, everything in the vehicle was going 110 now. Because if you stop a car instantly, everything inside the vehicle now picks that speed. Yeah. Not through. They had to pull them out. But he's also, they've come across people that have got in collisions and they look perfect. They don't even look like they've been, but just their lungs and their heart hitting their rib cage that fast kills them. So head-on collisions, you don't survive them. I don't care how many airbags you got, right? But if you're driving 30, you'd be like, boink. What are you doing, man? Why'd you run into me, right? Okay, but I digress. Now what happens? For a half an hour, we will drive at 80. Just like a half, right? Okay, now goes up to 110 for 1 hour again. So we go from 1.5 to 2.5. So this would be like 2, and this is 3. Okay? Okay, at what point does she go to 0? She goes to 0. So basically, slows right down, and boom, right there. Oh no, that should be at 2.5. Yep. Yeah, it does. Yeah. All you have to do is all you guys just hit your back arrow, and it all goes away. Okay, I don't know why you guys whine so much. It's a back arrow. It's like my favorite button on Microsoft Word. Okay, now, then what am I doing? So, if you went for 2 hours at 0, all the way to 4.5, right? Then what happens? So go up to 100, which is right there. So we go up to 100 for the rest of the time. We don't know how long, it doesn't say. She returns home. Ah, very good. So how long should it take? If it was 2.5 there. Okay, so at this point, Okay, maybe we don't really know. But that's what the graph would look like. Does this make sense? This is her speed versus time. Now, let's do a distance versus time. Okay. Now, let's do at 1. How far has she gone? 100 kilometers. Now, you guys, I don't know if you know this formula. D equals RT. Distance equals rate times time. So, distance equals the rate is 100 kilometers per hour. Time is 1 hour. See the hours cancel, and we are left with 100 kilometers. So, in 1 up there, she goes 100 kilometers. Let's do 2. Okay, D equals RT. She goes 100 kilometers in that hour. Okay, number 2. What is the rate she's going there? 80 kilometers per hour times 0.5 hours would give you 40 kilometers. Okay, let's talk about 3. $110 times 1. Oops. Here, I'll go up a bit so you can. So 110 kilometers per hour times 1 hour equals 110 kilometers. Okay, and did we number 4? Yeah. What would 4 be? 4 is 100 times. Now, how did we establish 2.5 hours? How would we establish that? Okay, here's a question for you. What's the distance to the location? Is it not 250 kilometers? So if all of this equals if this equals 250, then she's got 250 home. Oops. So 100 kilometers per hour. Now we know the distance. So the other formula, well, you can still have that. I just want to write this formula. If D equals RT, I'm trying to find time now. Or sorry, I'm trying to find T. So I'm trying to find so I got 110 kilometers per hour. So I know D, I know R. Okay, so I just know that this last part is 250 kilometers. 4. It has to be, right? Because if the first part was 250, the second part would have to be 250. Okay, now let's do a graph. So on the bottom, what kind of time? Probably the same time we're looking at, right? So 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 1, 2, 3, 4, 5, 6, 7. Okay, oh, bad. Start at 0. What am I doing? 0, 1, 2, 3. Make sure I'm recording. 4, 5, 6, 7, 8, 9, 10. And I'm not having a good day. 1, 2. Every half hour, right? 3, 4, 5. Okay. And what should our distance go up to? Distance from home. So the distance from home, the greatest is 250. So let's go by 50s. So let's go 50, 100, 150, 200, 250, we'll go up to 300. Okay, so at 0 time, how far is she from home? She's 0. 0 distance, 0 time. Okay? Now, first she goes 100 kilometers in how much time? So we go from here to here in 1 hour. So 100 kilometers an hour, 100 kilometers in 1 hour. Now I am going 40 kilometers in half an hour, right? So 40 kilometers in half an hour would be about there. And do you see how the slope decreases? The slope decreases because it's going slower. Then what happens? My slope didn't. Oh, you're talking to him. Well, I can't. I'm on tape. I can't talk now. What am I doing next? 200? 250, right? So the next one, I'm going 110 kilometers in 1 hour, right? So that goes from 1.5 all the way to 2 so 110 will get me to 250 at 2.5. Okay. Now, oh, that's supposed to be at 2.5. I'm not liking that. Okay. Now, what do I do now?
2 hours away. 2 hours that.
So 2 hours at that. So I got 2.5, 3.5, 4.5. This is my distance away from home. It has not changed. Okay, now what happens? Two and a half hours like that, yeah. Yep. Now, do you see how the speed versus distance from home is very different? The next one is distance versus time. Not distance from home, but distance traveled. Okay, well, how far are my distances? The first distance is what? 100 kilometers. Then my second distance, how much was done at that second interval? 40. My third is 110 kilometers. My fourth is, okay, or you can say 0, because there's that whole time that I have not traveled. Okay, and then 5, we'll say, is 250 kilometers. Now, by our addition skills, how far would the odometer say? 500 kilometers. Now make sure your graph says 500 kilometers. So if I was to do this and this, I'm going to do my times the same. 0, 1, 2, 3, 4, 5, 6, 7. I'll just put ticks in between. Okay. What should be on the side besides kilometers? What should be my maximum? Min would be 0. Max, 500. Okay? So let's go 100, 200, 300, 400, 500. You should actually always go higher than you need. So there's 600. So 100, 200, 400, 500. So this is distance traveled, right? So this is what, if you would push if you ever charge for mileage, like a lot of people that travel that get paid for mileage, they hit the odometer, there's the, just reset, not the main odometer, but your tracker, and then they just, when they get home, they just chart the kilometers, right, in a book or an app. Now, so in 1 hour, we have traveled 100 kilometers. Right there. And then in a half an hour, we traveled 40. So it would be like right there. So that's 1. That's 2. Then we did 110 in how many hours? 1 hour. So 110 for 1 hour. So if we're at, where are we going to be next? 250, yep. So 2.5 at 250. No, it's an hour, right? So from 1.5 to 2.5. And that is going to be 100. So we should be at about 250. Okay, then what happens? What would the odometer be doing for the next 2 hours? It's staying the same. So that would be 2.5 to 4.5. Right there. So that would be 4. Right, so it kind of looks like above. But the change now, that last part, right? So that would be 250 to 500 in the 7 hours. Okay, so this is a really, really good example of know what your increments say. And know what your X and Y are, because if it's distance versus distance from home, they are different. Okay, so let's finish off with just looking at graphs. These are your 3 graphs you should always kind of know. This is your constant rate of change. Now it can be going up or it can be going down. It doesn't matter. You also have where it's not constant. And then when you have no change. Now, if you were driving down the highway, what kind of change? Okay, you would say constant. A bus pulling away from a curb. So, yeah, because you're accelerating. Your speed would not be constant, right? So not a constant rate of change. A sprinter running a 100-meter dash. What about that acceleration, and what about burning out at the end, right? But if you're in good shape, you wouldn't burn out at the end, but still you have that acceleration. But so you would say beginning, not. You don't need 2 eyes. Okay, but once running, you would say it's pretty constant. Nothing's perfect, we know that. A cockroach population doubles every 12 years. It actually is not. Because this is the graph that cockroaches make. So it is a constant change, which means acceleration could be constant, but speed of the amount is not constant. So this is not constant. Okay, and the amount of money earned compared to the number of hours worked. It's constant. Okay, so there's your not going to be homework, because you're all going to finish in class. Oh, you will be happy. You'll be happier because you've accomplished something today.
I'll be the happiest.
Hold, I gotta stop taping because whatever you say right now could be help.